Welcome back. So we were talking about training techniques and heuristics. We talked about initialization, normalization, and also automatic differentiation. Today we're going to talk about another very important technique that we use when training deep neural networks, and that's the concept of regularization. What's the idea? Again, what we are doing, our main goal is to build models that can identify, learn, and leverage patterns from training data to unseen data. So essentially, we want models to not just fit the training data well, but be able to perform really well on data that they haven't seen. Okay, so therefore, we want the not only we want the training loss to be low, we also want the test loss to be low as well. Okay. How can we sort of ensure that? There are, I would say, very important results that we can leverage from classical machine learning theory. Okay, so at high level, these kind of results suggest that if you're hoping to reduce the generalization error, meaning that if you want to ensure that your model performs well on unseen data, this could happen as a result of what we call regularization. You regulate the power of the model. Okay, so basically you want to constrain the sort of the values that our parameters might take. Okay. Now, given that we are using parametric models, okay, so if I constrain the values that the parameters can take, therefore, intuitively, I'm also constraining the capacity of the model. I'm reducing the capacity of the model. So therefore, the classical ML theory seems to suggest that in order to ensure you have good generalization, you should reduce model capacity. Okay, and this view has certainly led to certain approaches and lots of development in the context of optimizing deep learning models. And we're going to talk about 3 approaches in this lecture. But my hope is to show that these 3 approaches, and certainly also other approaches, are intimately connected. And the perspective we're going to take to show this connection is what I refer to as the noise injection perspective. Okay. All right. Now, so therefore, this is our what we mean by regularization. Limit the capacity of a model. Okay. Certainly, this is at odds with what we are doing in practice, especially nowadays, right? So where we have very, very large models, highly overparameterized. And what we have observed is that these models are overparameterized, therefore they can perfectly fit any training data. But not only the training loss is 0 or near 0, as we keep increasing the overparameterization level, the generalization performance also improves. Okay, so this is basically therefore a little bit contradictory to the classical ML view that we also use as one of the motivation for this course. But as we're going to see in future lectures, there are still some connections such that one could say under certain assumptions, overparameterization also leads to certain form of regularization. Okay, and this is something we're going to talk about, as I said, in future videos. For this lecture, we're just gonna assume that, again, we are following the classical ML view. We want to regularize the model, meaning that we want to limit the capacity or the learning capacity of a certain parametric model, such as, let's say, a feed-forward neural network. Okay. All right. So let's talk about the first method, method A, and that's called L2 regularization. Okay, so we want to limit again the values that the parameters can reach. So one way to do that is to introduce L2 regularization. Okay. In particular, we want to constrain how large the parameters can get. Okay. So therefore, what we'll do, instead of minimizing the average loss as we've been doing so far, we're gonna add another term to it. Let's say lambda times the Euclidean norm of the parameter square. Okay. That's why it's called L2 regularization, because you are basically augmenting the loss with some Euclidean norm of the parameter. Here, lambda is basically called the regularization parameter. Okay, so this helps us to control how much we want to limit the capacity of the model. Intuitively, as lambda gets larger and larger, we are imposing this L2 regularization more and more. Therefore, we are limiting the capacity of the model more and more. Okay. Okay. So another, I would say, nice property of using L2 regularization is that it helps us to make the landscape of the loss looking better. Okay, so let's look at this from a purely optimization perspective. Our original loss could be highly non-convex, right? Because the model architecture is highly complex. This part, on the other hand, is a very simple function. It's a convex quadratic function. Okay, so even though the original loss could be very difficult to optimize, loss plus this L2 regularization could actually be easier to optimize thanks to the nice properties of the quadratic function. Okay, so therefore we expect that if my regularization parameter, let's say, is adequately large, by adding this term, I may get rid of all the unstable points, such as weak saddle points, maybe local maxima, maybe even tiny local minima, things like that, such that at the end of the day, this nice, let's say, area that contains my global solution remains. Okay. So therefore, intuitively adding a nice, strongly convex regularization term to the loss helps us to improve the landscape. Okay. This is obviously good for optimization, as we just talked about, but also it is good for generalization. Okay, and this is something that I'm going to get back to later on in this work. So essentially, if I have, and the idea is quite intuitive, right? So if you have a function that is that has a good landscape, basically means that it has a very low sensitivity with respect to the changes in the input. If I change the input slightly, the value of the, let's say, the loss is not going to change much. That is to say that if I change the training data slightly to get let's say a test data that I haven't seen before, my model is still going to work very well. Okay, given that the model is not the model, and therefore the loss is not as sensitive with respect to, let's say, small changes in the input. Okay. But so as I said, I'm going to talk about that. But let's first talk about again the improvement that we get on the landscape, and therefore, let's say, better optimization. Here I have a highly non-convex loss function. So this is the original loss. Let's call it f of x or f of w. And what I'm doing, I'm adding a regularization term to it, such that as I move in this direction, I'm increasing the regularization parameter. I'm increasing lambda. Okay. So as you can see here, as lambda increases, this this local optimum completely vanishes. Furthermore, this local maximum completely vanishes, such that when my lambda is large enough for this function, the regularized loss doesn't have any local minimum. It also doesn't have any local maximum. So therefore, whenever I initialize, I should be able to calculate the optimal solution of the regularized function which is here, quite efficiently and quite easily. Okay, but what's the catch? The catch is that if I call this guy W tilde, there is some bias. Okay, so this guy is the optimal solution of the unregularized problem, but as a result of adding regularization, there is some bias here. Okay, but what we are doing, we are basically gaining some bias to make sure that there is a huge improvement in the landscape of the function. Okay? All right, so this is from the perspective of optimization, but let's also see why adding this regularization helps us to limit the capacity of the model. Okay, so let's consider two cases. Okay, so again, I have this regularized loss where I have two regularization parameters, where the first one is larger than the second one. It is not very difficult to actually show that if I call the optimizer of each one W tilde j, as I increase lambda, the size of the optimal solution reduces, such that at the limit, in the extreme case, when lambda goes to infinity, W becomes exactly 0. Okay, so therefore, as regularization becomes stronger, the optimal model becomes smaller and smaller. Okay, so therefore, given that we are constraining the value that the optimal parameters can take, we are therefore reducing the capacity of the model as a result. Okay, so that's again something we can do very easily using some of the techniques we've talked about in the class before. Another thing we can do is to actually characterize the bias that I mentioned previously. Okay, so let's say that W star is the solution to the unregularized problem. Okay, as we said, by adding regularization, L2 regularization in this case, we are improving the landscape, but we are gaining some bias, meaning that the solution to the regularized problem is not exactly the solution to the unregularized problem. What is that bias? Well, we can characterize it by imposing some assumptions on our loss function. For instance, if we assume that the loss function is L smooth, meaning that the gradient is L Lipschitz, we can lower bound the bias. Okay, so this is how I define the bias, the relative change in the solution compared to the unregularized case. And the bias is going to be something like this, where lambda L is basically the ratio of lambda and L. So this is a function that is increasing in lambda. So if you plot it, it's easy to see. So what this means, therefore, is what we expect to happen. As lambda increases, we are constraining the model capacity, we are improving the landscape, but the bias increases. All right. So as I mentioned, this is helpful. Adding L2 regularization is quite helpful in terms of improving the landscape of the function. Now, let's see how does that impact the optimization process. Okay. So let's imagine that we're going to use a nice simple method such as gradient descent. Okay. So we want to see what's the update for the gradient descent when we apply it to the regularized problem. Okay, so what is a regularized problem? Again, we have the original loss, minimize the average loss, but we add this L2 regularization term. It is not difficult to see by taking the gradient that the update of the gradient descent is going to be given by this expression. If I factor out Wt, I'm going to arrive here. Okay. Now this is called in the literature introducing weight decay, and the idea is that if lambda is a small, okay, and eta is also a small, this coefficient here, 1 minus eta lambda, is something that is always between 0 and 1. Okay, so therefore, what I'm doing, instead of just going into the direction of the negative gradient to minimize the function, I first decay the parameter and then go into the direction of the negative gradient. That's why it's called weight decay. Now, what we showed here is basically that weight decay, gradient descent with weight decay is basically exactly like applying gradient descent to the regularized problem. Okay, and this certainly is true that when you use simple methods like gradient descent or stochastic gradient descent and equip them with weight decay, what you are doing is basically you are applying those simple methods on the regularized problem. However, it's not true in general. So if I give you like an arbitrary algorithm, such as Adam, and then I apply weight decay with that algorithm, the result is not necessarily equivalent to applying Adam to the regularized problem. So this is something, a distinction that is quite important and also leads to different algorithms, right? So for instance, this method that we will talk about, you can apply it to the regularized problem. You can apply its weight decay version to the regularized problem, or you can just apply the weight decay version directly to the unregularized problem. All of these are different learning or training problems. Okay. All right. So that's basically the first method, L2 regularization, and how it's also connected to one concept, one practical concept such as weight decay. Now let's talk about another method, and that's called early stopping. So the idea is that when you are doing a training, you maintain a validation set, which is basically a bunch of data points that you are not using in your training. You are not using them to update the parameters of your model. Okay, and then you'll monitor how the model is performing on this validation set. So you're going to monitor the validation loss. You're going to continue training until the validation loss starts to increase. Then you're going to stop. So in particular, you're going to stop earlier than what you would originally do if you didn't have any validation set. That's why it's called early stopping. So here is the idea. Let's say that this is the training curve, and this is the evolution of the validation loss. Okay. So if I weren't doing any early stopping, let's say I would stop here. Let's say at epoch number 100. But given that I'm doing early stopping and I'm monitoring the validation loss, when I hit here, I'll see that the validation loss starts to go up. So I'm going to stop the training here, let's say at epoch number 50, or earlier than what I originally had in mind. Okay. Now again, this is some sort of regularization. Why? Because we are sort of restraining the model to reach its maximum learning capacity. Okay. So this is exactly the definition of regularization. Now, there is actually a connection between L2 regularization and early stopping. And to discuss that connection, let's use a simple loss function, in particular a quadratic loss function. Okay? So let's consider a convex quadratic loss function, which has this form. I'm missing a transpose here, where the optimizer is nothing but W star, and you can show that quite easily by just taking the derivative and set it equal to 0. Okay. Now for this loss, it's not easy. It is easy actually to show that for gradient descent, the update is going to follow this expression. And here, for simplicity, I'm just assuming that I initialize my parameters as 0. Okay. Now, I'm assuming that this is a convex quadratic function. In particular, this H matrix is a positive semi-definite matrix. So we know from linear algebra that this has a spectral decomposition, which basically means that there exists a unitary matrix U and a diagonal matrix lambda, such that H is exactly given by this product. So what we can do, we can leverage this spectral decomposition with certain steps that I'm skipping here. They're not difficult. It's just some, I would say, algebraic manipulation. What we can show, however, using these ideas, is that for the gradient descent algorithm without any L2 regularization, the update is going to satisfy this expression, okay? So this is basically the parameter at time t of the original problem where there is no regularization. Also, what we can show is that for the regularized problem, there exists a relationship between W tilde and WT, okay? So if we hope to establish an equivalency between early stopping and L2 regularization, therefore, I want these two to be the same, okay? So meaning that if I stop early, let's say at some iteration t, the solution is roughly the same as the optimal solution of the regularized problem. It turns out that we can get this equivalency if there exists this dependency between the regularization parameter lambda, the iteration or the epoch at which we stop, capital T, and the reciprocal of the step size, okay? So what this is saying is that if I fix the learning rate, stopping early is like employing a larger regularization, employing a larger lambda, okay? So therefore, they both have this regularization effect. So in some sense, they are sort of equivalent. So it is like if you are doing early stopping, it is in some sense equivalent to just apply a regularization to your original loss without doing early stopping, okay? Obviously, what we just mentioned here is true for quadratic loss functions only, but what we hope is a certain this equivalency to transcend beyond the simple context to more complicated loss landscapes, such as those we deal with when we train highly complex deep brain models. All right, so let's now talk about the third method, and that's called dropout, okay? So this actually is something that's originated specifically from the context of neural networks, okay? So what do we do? So when we are doing training, we are going to drop some of the neurons at random. And by dropping, I mean that we're going to zero out p fraction of them. So what this means is that, let's say with dropout, if I had the output of some neuron, let's call that hi, I'm going to set that to be 0 with probability p, and then I'm going to basically return the original value divided by 1 minus p with probability 1 minus p. So this normalization is there to ensure that the outcome of this randomized operation is an unbiased operation, okay? Such that on expectation, I'm not doing any change to the neural network, right? So on expectation is as if I'm not dropping anything, okay? So again, this is a regularization. Why? Because when we drop neurons, we are reducing the learning capacity of our model, okay? So we are restraining the model to reach its maximum capacity. And this is exactly regularization, okay? So here is how dropout will look like then. So let's say this is the original model before dropout. And then I may basically, again, due to this random process, I'm going to drop the second and the fifth neuron. So I'm going to completely zero them out, which means that there's not going to be any connection from the input to these neurons, and there's not going to be any connection from these neurons to the output, okay? So one minor or side remark is that in testing, we typically disable dropout. And this is exactly what we, like how we approach applying batch normalization. We employ certain randomization during our training, but we make sure that our operations are basically deterministic at test time. However, there are some applications that we indeed also leverage dropout at test time or during inference. For instance, one application is uncertainty quantification. So the idea is that if I give you a model that is let's say completely trained, by randomly dropping out some neurons, I'll be able to, let's say, get a distribution for the output. And then I can use that distribution to talk about, for instance, what's my confidence in terms of the predicted values, right? So, and things like that. And this is the concept of uncertainty quantification. So dropout could also be useful in those different applications, but for us that we are talking about regularization, to make sure your model is going to generalize well, you only use dropout during training. Okay, so that's our third method. Okay, so we talked about L2 regularization, earlier stopping, and we actually show that under certain conditions, L2 regularization is similar to earlier stopping. Now we're going to also establish a relationship between L2 regularization and dropout. So in particular, we're going to show that under certain conditions, dropout is basically like applying L2 regularization. Okay. But we're going to obviously make our study a little bit easier. So let's see first what dropout is doing, and let's try to simplify dropout to make sure that we can perform a simple analysis. So what dropout is doing is essentially injecting noise into our model, okay, and therefore our learning problem. So what's the noise? The noise is basically which of the neurons I want to zero out. And this noise is basically independent of the activations, okay? But it is multiplicative in nature, okay? So because to zero something, I'm basically multiplying that with a random variable that can take a value as zero, okay? But we're gonna basically make sure for our analysis, we're going to relax this multiplicative nature with some additive noise, but we're going to still retain the independent nature, as well as the fact that we are injecting noise in the first place into our learning problem, okay? So we're going to use a simpler model to show the regularization effect of noise injection, okay? So let's consider a simple linear model. So I want to minimize this loss to basically have a good fit to the training data. Okay, so what's my loss? It's a linear model for, let's say, regression. So I'm minimizing the square loss. So this is basically the average loss that I'm minimizing. Okay. Now, think of this H here as the activation. Okay, so this is the activation that in dropout we are injecting noise to it. So which means that we are going to zero it out with certain probability. So here, therefore, we're also going to inject noise to this activation H. But as I mentioned, we're going to use an additive noise as opposed to a multiplicative one. So meaning that H is now going to go to H plus some E. E is the noise which is independent of the X and also H. It's a zero mean, okay? And it's, let's say, has certain covariance, okay? So this zero mean nature is also, again, something like what we have in dropout, right? So where we normalize by 1 minus p to make sure that we are not incurring any bias as a result of this random operation. So that's why here we also use a zero mean noise. Okay. Now this is basically the covariance matrix. Covariance matrix you may know from your probability courses that is a positive semi-definite matrix, which means that there exists some matrix A such that I can write down the covariance in this form, okay? Now, let's consider the following new loss. I take the original loss, I inject some noise into my activation H, and then I take an expectation with respect to this new random operation. So my new loss, therefore, not only takes the expectation with respect to Z, basically it still is an average loss over the trained data, but it also takes the expectation with respect to this random noise that I'm injecting into activation. Okay. Now, using very simple steps like expanding the quadratics, using the fact that noise is independent and it's zero mean and things like that, we'll be able to show that this new loss is exactly like the original loss plus Euclidean norm of AW squared, such that if, let's say, I use like a noise with a covariance matrix which is identity, okay, such that so if sigma is equal to identity, therefore this term is going to be exactly L2 regularization. Okay. So therefore, under these, again, like simple assumptions, what we have established is a very nice connection between dropout and L2 regularization. Notably, what we are talking about here is that injecting noise could be helpful in terms of, let's say, regularizing the model capacity, okay? And given the equivalency between noise injection and L2 regularization, and the fact that L2 regularization was helpful in terms of improving the landscape of our function, we might expect that injecting noise could also be helpful in terms of improving the landscape of the function from a purely optimization perspective, okay? And indeed, that's true. In a lot of cases, we inject noise to, let's say, get rid of saddle points, get rid of unstable points, make sure that our algorithms can avoid bad solutions. Okay, so therefore we inject noise to improve the landscape of the function. In particular, we actually saw a similar idea here when we talked about Gaussian smoothing and zero-order SGD. In that context, we said that if you want to optimize a function without accessing the gradient, you can optimize its a smooth version instead. The smooth version was basically taking the function and then finding the convolution with the PDF of a Gaussian. This is exactly that. Okay, so what we are doing here is that we are taking the original function and then performing some sort of convolution. Okay, and if you recall, we call that Gaussian smoothing because the smooth function improved the sensitivity parameters of the original function, such as the Lipschitzness and the smoothness constant. Okay, so therefore, again, we are seeing that noise injection can indeed help improve the landscape of the function. Okay, so therefore we can sort of generalize this idea of noise injection, right? So for the purpose of, let's say, both improving the landscape and also for the purpose of improving the generalization capability of our model, okay? So previously what we did, we injected the noise directly into the activations, right? So what we can do is that we can actually inject the noise into the parameter itself, okay? Also, instead of taking the expectation with respect to the random choice of noise, we can basically apply a deterministic worst case noise, where the noise is basically bounded, okay? So we have two options. So one option is that, again, so I'm directly injecting noise into W. But one option, my noise is random, and therefore I'm introducing this expectation with respect to this new source of randomness. Another choice is that I inject the noise, but I'm looking for the worst noise. The worst noise that is still tiny. So therefore I'm enforcing this constraint on how large the noise can get, okay? Now the second formulation is interesting, and with certain approximations, for instance, using the first order Taylor approximation, is going to lead to this formulation. Again, this is some sort of regularization, but instead of regularizing the original loss with the L2 norm of the parameter, what we are doing, we are regularizing how large the gradient of the function can get, okay? So basically, again, we are regularizing the sensitivity of the model. If you think of the gradient as some notion of sensitivity, which is, I would say, intuitive, we are explicitly imposing a constraint that the gradient shouldn't be large. Now, this is called sharpness-aware minimization, or SAM formulation, and it's proposed, and it's a very, I would say, effective and popular approach to improve the generalization property of neural networks. And the way that they approach this, again, is to by penalizing the sharpness or sensitivity of the loss, okay? Now, here we are using the gradient or norm of the gradient as a way to characterize how sensitive or sharp a specific loss function or loss landscape is, nothing stops us to go to higher order derivatives, right? So for instance, instead of the norm of the gradient, I can think of some norm of Hessian, right? So I can, for instance, talk about the maximum eigenvalue of the Hessian or the trace of the Hessian or things like that, okay? And these, one could refer to them as higher order sharpness severe minimization or higher order SEM, okay? And those will also be effective in terms of improving the landscape as well as improving the generalization. All right. So now let's talk about why improving the landscape could help with generalization, okay? In particular, let's consider two cases. I have two minima, and one of them is basically a sharp minima, meaning that when I deviate from this point, the loss value is going to go up quite drastically. The other one is basically a minima in a very flat region of my loss landscape, meaning that when I deviate slightly, the loss value doesn't is not going to go up drastically. Okay, so the solid line is basically representing my training loss, the landscape of the training loss, and this dashed line is basically representing the landscape of the test loss. Okay, now again, given that the training data is not exactly equal to the test data, I expect that if my model is performing, let's say, very good on the training data, it may not perform as well on the test data. However, if the distribution of the training and test are more or less the same, these two loss functions should look more or less the same. In this case, let's imagine that the test loss is basically a shifted version of the training loss. Okay. Now, here we can immediately see why finding a solution in a flat region is going to be better for generalization, and that's because of lower sensitivity. Okay. So, given this shift, if I found a solution here, it's still going to do very well on test data as well. So therefore, I'm going to have a really good initialization. On the other hand, if I found a solution here, I'm going to basically do very badly on the test data. So therefore, a very bad generalization. So therefore, by regularization techniques, such as incorporating L2 regularization or sharpness severe minimization, we're going to make sure that we're going to find solutions that are that tend to be in the flat region of a landscape. Therefore, those solutions are going to generalize better as well. So this was our lecture on again, one of the most important techniques when training neural networks. And we try to sort of connect these regularization techniques from the perspective of optimization. And we also saw the importance of noise injection. In future lectures, we're going to start talking about some key ingredients that we use in training algorithms and optimization algorithms. I'll see you next time.